we are going to talk about something I've wanted to make a video on for a long time because this is essential to any college level chemistry, biology, biochemistry, organic chemistry, etc. And especially if you're prepping for the MCAT, this concept is essential. So we are going to start the concept of chirality and stereoisomers by looking at a mirror. So if you look at this chair on the left of the screen, it's going to have a mirror image, and let's pretend that this mirror image comes to life and scoots over and overlaps or superimposes onto this original image of the chair. Well, if you do this, they fit exactly into each other, right? They're the same. On the other hand, if you look at those hands, no pun intended, and you try to overlap them, you don't have to just look at the picture. You can do this in real life with your real hands. If you try to overlap them, the closest you can get is like the clapping or praying position, and all the fingers are kind of in the same places, but on one hand, your knuckles are facing to the left, on the other, your knuckles are facing to the right, same with your palms, they're facing different directions. So your hands, even though they're mirror images, they're not the same. They're not superimposable onto each other. So that, in chemistry, we term enantiomers. So you might have heard of structural isomers, of cis-trans or geometric isomers. Enantiomers are just another kind of isomer to add to your toolkit. So if we look at this with an actual molecule, we can see we've got a central atom that's usually going to be a carbon, very occasionally a nitrogen, and it's bonded to these four things that are right now not atoms but just colors. And we're gonna take the mirror image of this and we're gonna see if they can superimpose. Well, obviously if we keep them as they are, they're not gonna superimpose. But well, you might think we are allowed to rotate. So let's rotate this so that the yellow is in the same place as it is in the original. And if we're rotating it around this way, we're kind of keeping the green in the same place, right? So we've got our central atom, we've got the yellow, which is now in the right place, we've got the green, but in this process, we've rotated everything to the right, right? So if we rotate the yellow all the way to the right, this pink, I don't have a pink, so I'm using red, it's going to end up in the back. And this blue is going to end up on the left. So this is kind of backwards because in this original thing on the left here, the pink was in the front. Now the pink or the red is in the back. So this little experiment did not work. We cannot superimpose these on top of each other. So these are enantiomers. They are mirror images that are not superimposable. Let's say that we take this carbon that's bonded to four different things and make it bonded only to three different things. We're going to make two of them the same. All of a sudden, if we take a mirror image and we rotate it, as shown here, we can get exactly what we started with, right? So this may be a mirror image, but because we can rotate it and then easily superimpose it, it is not an enantiomer. These are not enantiomers. They're just the same molecule, but we turned it around in space, right? So when we have an atom where the stuff around it makes enantiomers, like this atom here, all the stuff around it made us a mirror image that was not superimposable, we call this chiral. And the centers that cannot do that, we term achiral, A meaning not. So if we look at this without just colors, but with an actual molecule, we've got this 2-bromobutane here. Well, the center that we are looking at is going to be this carbon, right? And it's bonded to four different things. We've got a methyl, we've got an ethyl, we've got this hydrogen that's kind of hiding back there, and we've got a bromine. Now we take the mirror image, it's on the right, you can see it here, and it's not superimposable where it is, right? No rotation, no manipulation, nothing. It's not superimposable because the bromines are obviously on the wrong sides. Well, let's do what we did with the color things and try to get this bromine to be on the right like it is in the original image. Well, if we rotate it this way, then the bromine is going to turn out on the right. But the thing is, in rotating it that way, the hydrogen, this little guy hiding back here, is going to end up on the front. In the original image, it was in the back. So it's not going to be the same thing. We're not going to be able to superimpose them. So these are enantiomers, and this carbon is chiral. So let's look at an example where we're going to figure out which carbons are chiral. And as we proved earlier when we looked at what's bonded to 4 different things versus what's bonded to 3 different things, a chiral carbon is going to be one that is bonded to 4 distinct groups. Now before we take a look at this, quick reminder, skeleton structures, every point is a carbon, every line is a bond. Carbons make 4 bonds. Anything that's a hydrogen, it's implied. So we kind of might have to draw them in. So when you're looking at this structure, we can start with eliminating all the ones that are not chiral. For example, this one is bonded to 2 hydrogens, right? Because it's bonded to 2 things here and here, and so the other 2 must be hydrogens. Same with this one, bonded to 2 hydrogens. Bonded to 2 hydrogens, bonded to 2 hydrogens. So that's like here where we were bonded to the 2 pink things. That means it's not chiral because if we flip it around with a mirror image and then we do some rotation, we can superimpose it and it's not chiral. And in this case, we're not looking at the whole molecule. There's a difference between a chiral carbon and a chiral molecule. Right now, we're going by the definition that a chiral carbon is bonded to 4 different things, and we're not concerned about we're flipping this whole big giant molecule thing. So, again, bonded to 2 hydrogens, bonded to 3 hydrogens, bonded to 3 hydrogens. Now, this one here is actually bonded to 2 methyl groups. This one and that one, right? So because it's bonded to 2 of the same thing, it's not bonded to 4 different things, and therefore it is achiral. We can also look at the carbons in this double bond. Carbons in a double bond are bonded to only 3 things. So by default, they cannot be chiral because they're not bonded to 4 different things. They're only bonded to 3 things. So this is achiral, and this is achiral. So again, the bonding, if you have a double bond, it's not bonded to 4 different things, so that one is also achiral. Alright, let's look at what we have left. So if we look at this one right here, and we look at the 4 groups, well, we see it bonded to 3 things, so the implied thing it's bonded to is a hydrogen, right? So we've got a hydrogen. We've got this giant groupy thing. Now, when you're looking at chirality and what a carbon is bonded to, you don't just look at the immediate atom. Like, oh, this is bonded to a carbon, and a carbon. It's not chiral. That's not how it works. Because if you go onward in the structure, you're going to see different things. Like there's a hydroxyl group, and there's a bromine group, and there's a couple of methyl groups, and a double bond. And that's very different than what the other carbons next to it are bonded to. So now we run into a bit of trouble because we have a cycle, right? It's bonded to a CH2 and a CH2, so it's bonded to the same things, right? Well, not really, because if we follow this around the circle, CH2, 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 carbonyl group. This way, CH2, carbonyl group. Those aren't the same journey, right? In one direction, we get to the carbonyl group sooner. In another direction, we get to it later. So, surprisingly, because it might seem like the cycle is one coherent thing, these are counted in stereochemistry as 2 different groups. So this carbon is in fact chiral. I'm going to kind of take these away. But we're going to signify the red means a chiral carbon. Come on. This writing is not working well for me. Sorry. So if we look at this one here, again, we look at the whole thing. So there's this whole groupy thing, right? We've got a bromine. We've got this whole circle thing. And then the 4th implied thing is a hydrogen. these are 4 different groups. Therefore, this carbon is chiral. So we can erase all this crazy stuff and put a check mark on that one, right? And that's it. We've covered all the carbons. So it's not as hard as it looks. Now, here's the other concept. You know how I said that a chiral carbon is not the same as a chiral molecule? Well, here's a prime example, is this cycle right here. So we are looking at this one. So if we look at this carbon, it's bonded to hydrogen, chlorine, and then we've got that cycle thingy again. So this way we have CH2, 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 and then we get to the chlorine. This way we get to it a lot sooner. And I like to use these substituents or things that come off of the cycle as kind of markers. So do I get to it sooner? Do I get to it later? If it's directly across and you get to it the same way, then you do have 2 of the same group. But that is not the case here. Here, you go one way around the circle, you get to it really soon. One way around the circle, you get to the chlorine later. So these are 2 different groups. We have the chlorine, we have the hydrogen. So this carbon here is chiral, right? And because we kind of had the same situation here, chlorine, hydrogen, chlorine sooner, chlorine later, that carbon is also chiral. So we do have chiral carbons, or carbons that are bonded to 4 different things. Now, usually what happens is that this leads us to a molecule where we make a mirror image and we cannot superimpose it, and that we call a chiral molecule. Well, in this case, that's not exactly true. Because if you see the mirror images here, they're the exact same. If we take this molecule and superimpose it onto that one, we've got the exact same thing. So a trick to how you can tell this is something called an internal plane of symmetry. So you see how I can draw this line right through the molecule and it's symmetrical on either side? And I can do the same for this one. I can draw the line right through and it's the same on either side. That's a clue to us that we have a compound with chiral carbons, but the compound itself is achiral. Now, cases like this, these kind of weird things with chiral carbons and achiral molecules, we call this a meso compound. And you'll see these occasionally, but hopefully not too often. If we look at the other case, this is a cis isomer, because remember, circles are kind of like double bonds. You can't move around them. So we do have this cis isomer versus this trans isomer. If we look at this case, we have the same things bonded to everybody. So chlorine, hydrogen, long trip to this, short trip to this, long trip to this. That's chiral, right? And then same thing here, chlorine, hydrogen, short trip to this, long trip to this. That's also chiral. And then if you look at the mirror images, this one actually works. It's a chiral molecule. If you try to rotate this around to try to make it fit, it's not going to work. Long story short, these 2 molecules in the mirror images are not superimposable, so this one is a chiral molecule. If you have a cycle, if you have the cis isomer versus the trans isomer, very often it's going to end up that the cis isomer is a meso compound, aka it's got chiral carbons but it's achiral, but the trans isomer is going to be a plain old chiral molecule. So now we're going to look at how we classify these stereoisomers. Because you know how we have like these IUPAC names for everything, and then if you have the name, you should be able to draw it out? Well, if I give you a name like 1-bromo or just bromo-iodo-chloromethane, which is this thing right here, you're not going to know which way to draw it. The right mirror image or the left mirror image, right? So let's find out how we classify these. So in RS stereochemistry, we are going to use a priority system. And the priority system works like, we're not counting this because there's always pretty much going to be a carbon in the middle. We're concerned with what's around it. And with what's around it, we are going to classify them by atomic mass. So, for example, if we look at a column of the periodic table, I'm not going to pull one up. I can't really in this app. So, what it's going to look like is you have chlorine, you have bromine, you have iodine, right? And as you go down this column, you get bigger mass, right? So we know that iodine is going to be the heaviest, then bromine, then chlorine. And hydrogen is the lightest element in the whole entire periodic table, so it's always going to be last priority. The next step of the RS naming system is we're going to put the fourth priority in the back. Now, this wedgy dashy thing might be new to us, so let's establish that the wedge means that it's going toward you, out of the page, into the space, out of the page, toward you. The dash means it's going into the page, away from you. So, putting the fourth priority in the back means making it a dash. So our fourth priority is already a dash in this situation, right? So that step is done with. The next step is that we are going to draw a little line from 1 to 2 to 3, and not to 4 because 4 is in the back. And we are saying that we are in the same plane, and that is not in the back. So now we look at this line, and we ask ourselves, is it clockwise or is it counterclockwise? Well, in this case, it's clockwise, because if it were a clock, it would go like 12, 1, 2, etc., and it would go clockwise. Now, when it's clockwise, we are going to term this isomer R. If we look at the mirror image, we can do the same thing with it. Iodine is the biggest mass, number 1. Bromine is the second biggest mass, number 2. Chlorine is the third biggest mass, number 3. And hydrogen is always going to be the littlest, number 4. Again, hydrogen is already in the back, or a dash, and it's number 4, so we are set up there. We draw our line from 1 to 2 to 3, and we see that this line goes counterclockwise, because if we're going to look at the clock, it's going to be backwards, right? So this one we term S. Now the R might be kind of obvious, we're going to the right when we're going counterclockwise. S, I'm pretty sure, is based on old Latin stuff where they used to think left and left-handed people and all that were sinister. So remember that R is right or clockwise, and then S is just the other one. That's the way I think of it. So things can get a little bit more complex. We can be bonded to more than one thing after the original atom that we're counting. We can also not have the fourth priority in the back. So if we look at these atoms right here, these two, ignore the circle one on the bottom, we can see that our fourth priority, or our hydrogen, is not in the back. So we're going to do a little rotation. And usually the hydrogen is not going to be at the top. It's going to be in one of the bottom 3, so you can just rotate in the plane of the bottom of the molecule, or of the tetrahedron, and we're just going to turn everything a bit to the right. And we get this thing here. So now we know this is 4, we talked about this is 4, but let's figure out the other ones. Now, always, when we're doing R and S, don't get overwhelmed with the whole entire group. For example, we're not adding up the mass of O and H here, because if we really look at it, it's an O, and the O is bonded to the H. So the only thing immediately bonded to the carbon there is an O. So we have this O, we have this C, and we have this C. So who's the winner? Well, oxygen is heavier than carbon, so this is going to be our number 1. Now we have a tie because we have a carbon and a carbon. And now we start to look at what it is bonded to. So this carbon at the top is bonded to 3 hydrogens. That mass, hydrogens, they're each about 1 atomic mass unit. So this adds up to about 3, right? This carbon down here is bonded to 2 hydrogens and a carbon. And again, if we look at this group a little bit bigger, we have the wedge, we have the C, and it's bonded to 2 hydrogens, right? And then this carbon has 3 hydrogens. So when we do our RS chemistry, RS stereochemistry, we're looking first at this immediate atom, right? Then we got a tie. Now we're going to look at what's immediately bonded to that. So that's going to be H, H, and C. So we haven't yet gotten to the level of those other 3 H's. But this H, H, and C add up to 1, 2 for each of the H's, right? We have 1 for each, and that adds up to 2. And then carbons are 12, so that gets us 14. So that means that this ethyl group wins. It's going to be number 2. And then this methyl is number 3. And then we already know that the hydrogen is number 4. And for some reason this has stopped working and it wasn't letting me draw number 3. But here's 1 to 2 to 3. There's our line. I'm going to draw it in a new color because we have a million things going on this page. 1 to 2 to 3. And it's counterclockwise. So think about it for a minute. What letter would it be? R or S? Okay, it's S. So there we go. We did one that was a little more complicated. So now we are going to do one that's a lot more complicated. And this one is the cycle, and we're going to use the same concepts that we used before. I'm going to make us a little room here. And this one has got 2 chiral centers. So we've got this one first, because this one, 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, 3 hydrogens. So we've got 2 carbons left that are chiral. So let's start with the one with the OH. Now remember that hydrogens are implied. So in this one, if we see that we always have 2 things that are lines or in the plane of the page. We have 1 wedge going toward us and 1 dash going out. So if we look at that carbon with the red dot, what's missing is our dash. We have a wedge. So we can draw our hydrogen in as a dash. And I made it that way on purpose because I don't want to waste our time rotating things around to get the hydrogen in the back. It is our priority number 4, right? 4. Why won't this thing let me draw? 4. Okay. So hydrogen is number 4. Now, if we look at this, we know that this is a carbon, right? And this is a carbon, and then here we have an oxygen. So actually we have the exact same situation as last time. Carbon, carbon, oxygen. Who wins based on atomic mass is the oxygen. So this is going to be number 1. Now we're figuring out 2 and 3. So I'm going to use a different color. We have carbon and carbon. This one has 2 hydrogens, right? And this one has 1 hydrogen. So when we're adding up what is directly bonded to these carbons, I'm going to call this carbon A and this carbon B. So carbon A is directly bound to 2 hydrogens and 1 carbon. So it's these 2 hydrogens and this 1 carbon. And we're not worried about what this 1 carbon I just circled is bonded to. We're not at that level yet. Only if we get another tie do we go there. So now let's look at carbon B. Carbon B is bonded to carbon, hydrogen, and carbon. So that's 1H and 2C. So now that we've got the hang of this a little, we might be able to eyeball it without looking at the periodic table and say 2 lighter things and 1 heavier thing versus 2 heavier things and 1 lighter thing. Carbon B is going to be our winner. So let's make us a little room again. And we're going to put down carbon B, or this one here, as 2. This one is going to be number 3. And now we can do our little line thing. And that is clockwise. So we are going to name it R. Right? Okay, so let's get rid of all this stuff. Give ourselves a little room because we still have a carbon left. So we have established that this one is R. So now let's pick a new color and let's work with this one. So this one, we have 2 lines, we have a dash. What's missing is a wedge, and that wedge is our hydrogen. Now I'm going to teach you a trick. We don't have to do all this crazy rotation in space. The trick when the 4th priority, usually the hydrogen, is in the front, is we go through a process like normal. We draw our line from 1 to 2 to 3, we say R or S, and then we just change it to the other one. So I'm going to demonstrate here. So priority number 1 is kind of a tie, right? Because we have hydrogen, carbon, carbon, not that carbon, this carbon, and that carbon. So we have 3 carbons. We're going to term them A, B, and C. So A is bonded to 1 carbon, 1 hydrogen, and 1 oxygen. And remember, we're not worried about stuff like the hydrogens on here and the hydrogen on there. So that's A. B is bonded to 2 carbons and 2 hydrogens. C is bonded to 3 hydrogens and 1 carbon. So you can pause this video and do the math yourself. I don't want to waste too much time on it, so pause the video if you want to try this out on your own. Okay, now what we're going to find out is that A is our winner. So A is going to be number 1, and then B is going to be number 2, and C is going to be our number 3. So actually we've ordered them perfectly. So A is 1, B is 2, and C is 3. And we're going to draw our line from 1, 2, 3, and that is counterclockwise. So we would term it S, right? But we said since the hydrogen or the 4th priority is in the front, we're going to switch it around and we're going to say that it's R. So we've got an R and an R. So now we're going to see how this comes out in the IUPAC nomenclature. So this one here is R. So if we're naming it, remember that our first carbon is going to be the one with the most important group. None of these carbons are bonded to anything relatively cool and interesting except for this carbon here, which is bonded to the oxygen. So this is going to be number 1. So then the other carbon that's bonded to a substituent here, because our longest chain is going to be this cyclohexane. That's going to be our longest chain, right? So the methyl is outside of that. The methyl is going to be a substituent. So that's going to be our number 2, 3, 4, 5, and 6, right? If you need a minute to pause this video and go back and review how IUPAC nomenclature works and longest chain and substituents and all of that, feel free to do that. But we are going to name this, and it's going to turn out to be 2-methyl cyclohexanol. Now I'm running out of time, so I'm going to say this very quickly. We are going to say that it is 1R, we put this in parentheses, 2R, 2-methyl cyclohexanol. Okay, I'm running out of time. This stupid app doesn't let me have a lot, so next time we're doing Fisher projections. Bye!